Okay, so in this video, I'll be doing the Benson electronics problem. So in this problem, you're manufacturing three components, components 1, 2, and 3, but you don't have enough capacity to manufacture everything yourself. So you're also considering subcontracting or purchasing the components from another manufacturer for a higher price. You have demands for each of these three components, and you have certain amount of time available. So here you don't have, not only have to keep track of how many of each component you make, you also have to keep track of how many of each component you purchase. So let's put all of that together. Let's begin with the first step, decision variables. Right, so what are the decision variables? So in this case, I'm going to say, I'm going to call them C1M is the number of component 1 manufactured that we make ourselves. That's why I'm calling C1M. Similarly, I'm going to have C2M, number of component 2 that are manufactured, number of component 3 manufactured. Similarly, I'm going to have C1P, number of component 1 purchased. So we either make it or we purchase it from another manufacturer. So this is obviously subcontracting. So similarly, we can subcontract for component 2 and component 3. So here you cannot solve this problem with just 3 decision variables. You need 6 of them. You need to keep track of how many you make yourself and how many you're buying from outside. And the reason for that is the price is vastly different. So if you make it yourself, component 1 is $4.50 per unit. If you buy it, it's $6.50 per unit. But if you look at component 3, it's way cheaper to make it yourself than to buy it from the outside, right? With that in mind, we can write the objective. So step 2 is the objective. The objective here is to minimize the total cost of manufacture and purchase. So you say minimize the total cost of manufacture and purchase. So let's write the cost of manufacture first, which is $4.50 times the number of C1s you make, plus $5 times the number of C2s you make, plus $2.75 times the number of C3s you make, plus $6.50 times the number of C1s you purchase, plus $8.80 times the number of C2s you purchase, plus $7 times the number of C3s you purchase. Right? So this is the total objective function. Minimize the total cost of manufacture and purchase. Right? Now the constraints are you have production time, assembly time, and testing and packaging time. So you have again 3 departments that you go through, and you have time component 1, component 2, component 3. But this is only for the components that you make. For the components that you purchase, you're just paying a flat price to buy the finished component. And of course, you have demands for the 3 components. So let's first write down the constraints for manufacture, production, assembly, and testing and packing. So you have 3 constraints here. So let's write the production constraint first. So step 3 is constraint. Right, so let's write the production constraint first. It's production. So it's 2 times the number of component 1s that you make, plus 3 times the number of component 2s that you make, plus 4 times the number of component 3s that you make, because production time is 2 hours for component 1, 3 hours for component 2, and 4 hours for component 3, or 4 minutes, I'm sorry. 2 minutes for component 1, 3 minutes for component 2, and 4 minutes for component 3, right? Manufacturing time in minutes. And it's total time that's available. So here you have to be careful because all manufacturing time is given in minutes, but all production time available are given in hours. So we have to do a conversion there. We'll convert everything into minutes, right? So 2, 3, and 4. Then you have 1 point. So, and the total time available for production is 360 hours. So 360 hours. So this has to be less than or equal to 360 hours. So 360 hours in minutes will be 360 times 60, which is 21,600 minutes. Right? So this is just for the ones that you make. Similarly, for the assembly time, 3. So 1.5 for C2M and 3 for C3M is less than or equal to 250 hours that's available. So it's 250 hours times 60, which is 15,000 minutes, right? And finally, packaging. Testing and packaging, 1.5, 2, and 5, and 300 hours. 1.5, 2, and 5. $300, so it's 18,000, right? 300 times 6. 18,000. There you go. So these are the constraints for manufacturing. Apart from this, we have demand constraints. So the demand constraints are right here. You need at least 6,000 units for component 1, 4,000 for component 2, and 3,500 for component 3. 6,000, 4,000, 3,500. Again, you have two options. So C1M plus C1P equal to 6,000. So you can either say equal to or greater than or equal to, but because it's cost minimization problem, you're going to do the bare minimum. So it will be equal to anyway. So I forgot the number. So 6,000, 4,000, and 3,500. Right? There you go. So you can either write equal to or greater than or equal to. Either way, you'll end up with the same answer. But these are the constraints. So let me just make sure I went through all the constraints. So production time constraints, blah, 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 blah. Yep, that's it. Okay. And then you have a couple of questions about sensitivity analysis that we'll come back to. But let's put this into the solver and solve it. So I'm just going to say this is Benson, right? Benson Electronics. Yep. Okay, there are 6 decision variables here. C1M, C2M, C3M, C1P, C2P, C3P. Of course, you have left hand side, right hand side. It's all those there. So let's begin. So first we have space for our decision variables. These are our 6 decision variables right here. Of course, the objective. Objective is cost minimization here. Let's see, what is this? Okay. Right. So the objective 4.5, 5, 2.75, 6.5, 8.8, and 7. Right. So those are my coefficients for the objective. And then let's write the constraints. So we have the production constraint. We have, so the 3 departments of production: assembly and testing and packaging. So let's do assembly and testing and packing. Of course, we have component 1, demand for component 1, demand for component 2, and demand for component 3. So let's write on the production constraints next. So for the production constraints, so this will be 2, 3, and 4. And for assembly, it's 1, 1.5, and 3. For testing and packing, it's 1.5, 2, and 5. Right. The right hand side is 21,600 here. 15,000 and then 18,000. They're all in minutes, right? 15,000 and 18,000, right? 6,000, 4,000, 35. So demand 1 and 1, 6,000, right? 4,000 for component 2, and for component 3 is 3,500. Right. Now these constraints, they are all less than or equal to constraints. So let's just copy like that. And these are all equal to constraints. There you go. So I have the coefficients all in. So let me write the formulas now. Some product formula. Again, it's the objective coefficient. Sorry, the decision variables, then the objective coefficients. These are dollar signs. These don't have dollar signs. Right. Now let's put the solver. Okay. Objective is here. It's cost minimization. So don't forget to click on minimization. The 6 decision variables are right there. Let me make that simplex. So 3 constraints, so 3 less than or equal to constraints. So left hand side is left hand side. So 3 left hand side, so H6 to H8 is less than J6 to J8. H6 to H8 is less than J6 to J8. And then of course the 3 equal to constraints is equal to, so H9 to H11 equal to J9 to J11. Take a cost minimization problem. Our objective is in H4. We'll have 3 less than or equal to constraints, 3 equal to constraints, and we click on solve. All right, so I'm going to generate the sensitivity report because we need it. This is the sensitivity report for Benson. And I'm going to put it after. Right. Now let's look at the solution. The solution says make 2,000 component 1, 4,000 component 2, and 1,400 of component 3 yourself. You buy 4,000 of component 1, you are not buying any component 2, and 2,100 of component 3 from your from the other manufacturer. So total cost is 73,550. This is the cheapest way of doing it. You cannot do it for anything less than 73,550 cost minimization problem. This is the minimum possible cost. You cannot do it for any less than this 73,550. Now, as far as the production constraints are you are using up all the production time, you're using up all the testing and packing time, but you're not using up all the assembly time. You have a slack. So slack is the difference between the time that's available and the time that you're using. So difference between the right hand side and the left hand side of a constraint. So that's slack. Now these constraints will have slack of 0 obviously because they're equal to constraints, they'll always be equal to. But in this case the slack is, this is 2800, which means that you have 2800 minutes of assembly time available. So you either have too many people working or you have extra time available that you can use to assemble something else or that you're working on. So you're working on a different project, or maybe you can reassign them to something else. So that's what's available right there. That's what slack is, right? So let's look at the question. So we saw the optimal units, how many units are produced, how many are manufactured. We saw all of that. Which departments are limiting Benson's manufacturing quantities? So manufacturing wise, we saw that we are using up all production time and we are using up all testing and packing time. So production and testing and packing are the two departments that are constraining what Benson can do. If they have more production time and more testing and packing time, they can make more themselves rather than buying from the outside. We definitely have we don't have this constraint is not a, it's not a binding constraint. So when slack is 0, we call these constraints binding constraints. So it's called binding. This is not binding. So this is a non-binding constraint. This is a binding constraint. So this is a non-binding constraint. We have some slack, so we have some leeway here, right? So that's what this question says. Now, which departments are limiting? So use the dual value to determine the value of an extra hour in each of these departments. So this is interesting to understand. So if you look at the report, now dual value is just another name for shadow price. Shadow price, dual value, they mean the same thing. So dual value is saying, so if you look at these two constraints here, so these are the two shadow prices that we have, right? So this shadow price here is negative 0.9 and this shadow price is negative 0.12. So what you're saying is that if you had 1 extra hour available for production, you can reduce the total cost by about 90 cents. So each hour is each minute, these are in minutes, I keep forgetting. So each minute is worth about 90 cents. So if you can, so because there's a cost minimization problem, negative shadow price is good because negative means that you'll be reducing your cost. If it's a profit maximization problem, you want positive shadow prices because you'll be increasing your profit. In this case, it's a negative shadow price, which means that for every hour that you have, every minute that you have extra, you will you'll reduce your total cost by 90 cents. So how much is an hour worth? An hour is worth 60 times this. So each minute is worth 90 cents. Each hour is worth about $54.38 approximately. So you're saying that if you have an extra hour for production, then you can reduce the overall cost by $54.38, right? Now, but the problem here is that you cannot increase this by an hour because the allowable increase is only 3200 minutes. If you have an extra hour available, you cannot increase your production time by an extra hour and keep the same numbers, because if you once you go above below the allowable decrease limit or above the allowable increase, so you know what, I'm going to change this. So let's calculate this. So minus the allowable decrease plus the allowable increase. So this is the range. So these are the range of values in which any of our arguments are valid. So what we are saying here is that so what we are saying here is that as long as the number of minutes available is between 20,000 minutes and 24,800 minutes. So from this point onwards, you can increase the number of minutes by 3,200 and still keep a similar solution, right? But if you change the number of minutes by more than 3,200 minutes, if you change it to say 3,600 minutes, 3,600 minutes, or 3,600 minutes, okay, so 60 minutes in an hour. So you can increase it by an hour. So I keep forgetting it's not in seconds, it's in minutes, okay. So as long as the number of minutes increases by more than 3200, then you don't know anything about the shadow prices. You have to recalculate the whole problem, change all your numbers and recalculate the solution. But as long as the allowable increase decreases within this range, you can use these numbers to calculate what your final solution is going to be. So your final solution is going to reduce by 90 cents. So, and we calculate that. So it's 90 cents per minute times 60 minutes. So it's $54.38. So that's how much your final cost is going to reduce by if you can add 1 hour to production. And if you can add 1 hour to testing and packing, you know what? Now, the reason why the 1 hour increase doesn't do anything here is because you already have a slack of 2,800 units. So it doesn't affect this much. So, but here for every hour, the increase in the decrease in price is only $7.50. So this is definitely a much better investment. So if you have time, if you have extra resources available, you should put it into production rather than in testing and packing. So I think that's the next question. Suppose that Benson has one additional unit. Oh, okay, no. So the extra hour, that's what we have. So let's look at part D. Suppose that Benson had to obtain one additional unit of component 2. Discuss what the dual value of component 2 constraint tells us about the cost to obtain an extra unit. Now, so if you look at the shadow price for component 2, it is 7.968, and that's the allowable increase, allowable decrease. So that's what so you're saying that for every component of extra 2 that you have to acquire, your price is going to go up by $7.96. So around about $8. So for every component of 2 that you have to acquire, you have to pay about around $8. Right? Now, why is this? So if you have to acquire an extra unit of 2, you might change your production mix such that you make some internally and then you make some of 2 internally and then maybe make less of 3 and buy more of 3. So there are lots of different ways of doing, but you're essentially saying that if you have to acquire an extra unit of 2, it's going to cost you $7.97. If you have to acquire an extra unit of 1, it's going to cost you $6.50. If you have to acquire one extra of 3, it's going to cost you 7 cents. $6.50 and 7, we know that. That comes from here, $6.50 and 7. But this is $7.97. This is different from the $8.80. That's because the final value is 0. You're not buying anything from the outside. You're making all of component 2 internally. That's because component 2 has the biggest difference between making and buying price. So there's a huge difference between that's $8.80 to buy it from the outside, but it's only $5 to make it ourselves. So it's a huge difference between these two. So you're making all of that internally. So if you have to make, if you need an extra unit 2, it might be that you will make unit 2 yourself and then not make, say, unit 3, but buy unit 3 from the outside. So you're essentially saying that for every unit 2 that you have to acquire, it's going to cost you $7.96 approximately, right? And this is valid as long as the increase and decrease are within this range. Okay, all right. So that's problem number, that's the final problem on the homework. So, all right, take care.